Today we're going to be talking about coordinate identities, specifically how they relate to the unit circle. So we will be relating those identities more specifically to trigonometric functions. We're going to start out with a simple proof and then look into a little bit more detail and get a little bit more technical to make sure that our math is correct. We talked about the fact that the unit circle can be written as a radius of 1 or a radius of r. So here we just have a triangle with a unit circle. You can imagine that there is a kind of a circle going around here all the way around. So we're just in the first quadrant for right now. So let's assume the radius is 1, or 1 radius basically, right? That's the simple version of the unit circle. And let's first talk about sine. That's the first identity we're going to learn. When we know sine of theta is opposite over hypotenuse, real quickly you can actually see that since the opposite side of the triangle is just the y value of your point and the hypotenuse is the radius, what is y over 1? Well, it's actually just y, right? So therefore, when we talk about y values in sine of theta is whatever the y value is of the point on the unit circle. And that simplifies a whole lot of things. It makes finding sine very easily. Got this on another page, and you can kind of see the math here. Sine of theta equals O over h, but opposite is y, and hypotenuse is 1. So sine of theta equals y. That's our first coordinate identity. Next one we have cosine. Well, cosine of theta is just adjacent over hypotenuse. You can quickly see that that would be x over 1, which would just give you x back. So when determining cosine on the unit circle, all you have to do is look at the x value of the point you're dealing with. So here's the work for that. Now tangent's even easier. Tangent's just opposite over adjacent. Since opposite is y and adjacent is x, that's all you have to do. Just as easy as the first two. Tangent then is just y divided by x, whatever your point is. And we're going to pull up the unit circle and different points and see how this applies. Cosecant is, it's hypotenuse over opposite, so it would just be 1 over y. Secant is hypotenuse over adjacent, it'd be 1 over x. And cotangent is x over y, adjacent over hypotenuse, so it would be x over y. So here's all your coordinate identities on one paper, on one sheet, on one page. However, I want to go into a little bit more detail because some of you are probably asking some important questions that we need to address. So let's take a look at that. So the first thing I want to address is what happens when we take this triangle and move it over into other quadrants. Let's go ahead and do that with this point. And these are going to be taking on, as you can see, a bunch of different angles. For example, what if we wanted to figure out sine of 120? I'm probably not going to be able to snap it exactly right. We'll just say that's 120. What happens to the sine of that? Well, first of all, you can kind of see that there are triangles formed in the second, third, and fourth quadrant. But in the second quadrant, we know just by looking before at the unit circle, the x values take on negative values. The y values stay positive. When we get to the third quadrant, y is negative, x is negative. And when we get to the fourth quadrant, the x value will be positive, the y will be negative. But the question, I always had was, do the coordinate identities still work in the second, third, and fourth quadrant? And the answer is yes, they do. Let's go to our unit circle app and just go to 120. Again, right now we're focusing on the radius equals 1, then we'll go into more detail when the radiuses are. We can still see that the y value is square root of 3 over 2, for example, at 120, and the radius is still 1. We can still see that this coordinate identity applies. It would just be the y value over 1. Pretty simple. Same for cosine. Cosine would just be x over 1. We can quickly see then that cosine of 120 would be negative 1/2. Now this brings up another important point. Can you have a right triangle at 120 degrees? Well, yes, you can. So the angle itself, 120, tells you exactly where to draw your triangle. So after you start here, we know the starting point is 0 degrees. After you go over 120 degrees, you then draw a triangle here. In terms of the right triangle, the 120 tells you to start down here, which is your reference angle, which would be 60 degrees. So there is and another way to think about it is 60 is nothing more than 180 minus, 120 is nothing more than 180 minus 60. So, you're starting right here because 120 tells you to go there. And this is kind of why I worked on this little applet this morning to show you that, the 120 or the whatever, 145 tells you where to draw your triangle. However, your theta also is basically this angle within the triangle, 180 minus whatever, which is your reference angle. So, yes, you can have coordinate identities in second, third, and fourth quadrant. And it all just depends on what this angle is. It can grow all the way to 360 degrees. So now I want to talk about coordinate identities in terms of r. So let's just say that the triangle is just a radius of r. Maybe it's not 1, maybe it's 30 or whatever. Well, in that case, you can see that your sine would be y over r. Okay, you can look at this in the first quadrant and tell that as well. Your sine would just be y over r. Now, this kind of leads us to why we usually write the unit circle just as 1. If I, go back and bring up my coordinate identities, we're going to take a look at those now. So let's assume then now that the radius is r. How can we show the coordinate identities there? Well, this is why, like I said, this is actually why we usually make the unit circle equal to just 1. So like we said, sine of theta would be y over r if we assume that the radius of our unit circle is r. Okay, so it'd be y over r. So in that case, y would be r sine of theta, right? And we could do the same thing for cosine. When the radius is just r, x would be r cosine of theta. Now let's pull up our unit circle again and put all this together. We're going to go back to unit circle app and we're going to make the radius equal to r. Now here's what's nifty about it. Since the x and y values are always going to be in terms of r, any point on the unit circle, so let's say we go here, you can actually just take the x value. So for example, let's say we want to do cosine of 45. Well, cosine of 45 would just be square root of 2 over 2r divided by r. The r's are going to cancel. Same for sine. Sine would just be opposite divided by hypotenuse. Square root of 2 over 2r divided by r. The r's are going to cancel, so it's going to leave you with square root of 2 over 2. So it's just the coefficient of that r. Okay, so technically, going back here to our sine and cosine, technically x is r cosine of theta, not just cosine of theta, but r cosine of theta. And technically y is r sine of theta. But because those r's cancel, we can look at y in terms of just sine of theta when the radius is 1. So that's why we typically draw the unit circle with a radius of 1. So let's just go back and change our radius to 1 now, and we can quickly see why we typically say sine is y, cosine is x. Just simplifies everything, makes a nice clean unit circle. But we need to understand both, because we know that all circles don't have a radius of 1. They have a radius of r, right, depending on how big or small the unit circle is. So that's it for coordinate identities and trig values. Go back one more time and take a look at those. So we have sine of theta equals y, cosine of theta equals x, tangent of theta equals y over x, cosecant is 1 over y, secant of theta equals 1 over x, cotangent of theta equals x over y. These will really help you, especially when we go to the next lesson, which is figuring out trig values of any angle. If you have any questions about this lesson, let me know.